So good morning. Can I start? My name is Limpouch. I come from Czech Technical University in Prague, and I will speak about numerical simulation methods for laser target interaction. Well, I found that the candidates had here no lecture about plasma physics, so I will give some essentials of plasma physics. I will give some essentials of numerical mathematics, and then I will get to numerical simulations more. Well, I would like to say that simulation is an important tool in scientific research. They are carried out to understand consequences of fundamental physical laws, help interpret experiment, can provide detailed information which is difficult to measure, and can design and predict new experiments. But I would like to stress that numerical simulation, it's not theory. It's numerical experiment. So we have experiment, simulation, and theory as a triangle. And even if analytical solution perhaps cannot be found, approximate theoretical models are still important. Often, as in experiment, we can get some result in simulation, and we don't know why. The system may be very complex, and the simulation can say something, and we do not need necessarily understand why that is the result. Well, what is the numerical simulation? Writing a program and using the computer to perform numerical experiment that can show time evolution of some nonlinear phenomena. Where linear problems, analytical solutions are available for most of linear problems, so numerical simulation is not necessary. However, often linear theory provides a theoretical basis for validating the simulation result. We can check whether our code reproduces the result of linear theory. Unfortunately, most plasma-based systems are highly non-linear. So numerical solution could provide theoretical basis for studying highly nonlinear and also, for example, high relativity system. Well, if I have laser interaction with matter, with target, and my laser is energetic enough, is intense enough, I would ionize any medium and I would get plasma. And because I expected that there would be some lecture about plasma physics before me, and it wasn't, I prepared a very short introduction about plasma physics. Well, plasma physics, you understand, it's some system which includes positive and negative charges, usually some ions, some electrons, possibly some neutral charges. And usual definition is that plasma must be quasi-neutral. We will see what it's in, and there must be some collective action by electromagnetic forces. So, first, what we need to know is Debye length. Debye length has, I show two meanings. First meaning, how far can electrons go with respect to ions by thermal motion? You can imagine that you have some plasma and you have here some sheet, and electrons went from this part to this position. So we have here ion charge, we have here electron charge. So plain capacitor was formed with area density sigma, which is in fact here from the electrons, minus E is charge of electrons, density of electrons multiplied by thickness of the sheet. Electric field in the capacitor is sigma divided by the electric constant of vacuum. So potential energy, I just multiply what force by electric field by delta, and I get the potential energy that electron needs to move the distance delta. And where is the source of the potential energy? Only the thermal energy that the electrons have. So this potential energy must be equal to Boltzmann constant multiplied by temperature of electrons, and I get this delta, and this delta is called electron Debye length. So this electron Debye length, as you see, is proportional to square root of temperature and inversely proportional to square root of density. Yes, so this is the Debye length, and if we say that quasi-neutrality of the plasma is approximately neutral at distances which is large compared to this electron Debye length. So if the plasma is much larger than this, we can say it's quasi-neutral, because the charge at such a volume is much less than the sum of negative, absolute value of negative and absolute value of positive. So the density of positive and negative charges can differ only slightly. Yes. So that's why we call it that plasma is quasi-neutral. The second meaning of the Debye length is that is distance at which a static charge is screened out inside plasma. So if I have some static charge, say perhaps some probe inside the plasma, and after some distance it's screened by other charges. If it's, for example, positive, electrons are attracted to the charge, ions are pushed out away from this charge, so we get charge that is neutralizing the static charge. So I say that at origin I have test charge Qt, and I solve Poisson equation. So Laplace on the potential is minus charge density divided by the electric constant. So the plasma charge density is electron multiplied by density of ion multiplied by Z is average charge of ions minus electron density. So that is Poisson equation. The potential phi is 0 in infinity, and then infinity is charge density is 0. So infinity electron density is some constant electron density and 0, which is there equal to Z multiplied by ion density. We use then in the field Boltzmann statistics. So we think that the temperature is high enough, that is much higher than Fermi temperature, so we can use the Boltzmann statistics. So Boltzmann statistic says that the density is Anther density multiplied by exponential of minus potential energy divided by thermal energy PE. So we get this for electrons, we get the same for ions. We put it here, and then we linearize this energy, so we assume that this potential energy is small to thermal energy. So instead of exponential of x, I get 1 plus x, yes? So if I get the solution, I get the solution for you see ordinary Coulomb potential of the test charge multiplied by exponent of distance divided by Debye length. So the potential is going down with characteristic lengths which is equal to Debye length. In my case, both electrons and ions are doing the screening, so I have the Debye length, which is 1 over Debye length square is 1 over the electron plus 1 over ion Debye length square. I have the electron and ion Debye lengths. You see that for statistic charge, if I had high Z, the ions screen at a smaller distance than electrons. But of course, if I had some charge that was moving, the ions were not fast enough to react, and I got screening mainly by electrons. But this is for ion charge. I get here electron Debye length as previously, and ion Debye length, and this is how fast the charge in plasma is screened. The screening is around any charge of plasma. Yes, if I have ion inside the plasma, it is screened if it's slow enough both by electrons and ions, if it's fast only by electrons. So there is something very basic parameter which is called plasma parameter, and it's basically the number of electrons in Debye square. So I multiply density of electrons by by volume of the Debye sphere, and I see that this plasma parameter it's scales the temperature to 3/2 divided by electron density by 1/2. So if plasma is hot and low density, I get this parameter very high. If vice versa, a dense low temperature plasma, I get this parameter low, and then it's not ideal plasma. If this parameter is high, I say that it's ideal plasma. Ideal because as the first approximation, I can use equation of state of ideal gas. If this parameter is high, then it means also that potential energy in field of electron at medium distance between electrons is much less than kinetic energy of electrons. So my electrons are weakly coupled. They move freely, and only little perturbation is due to potential on energy of interparticle interaction. I can speak this is our weakly coupled electrons, but there is more probability that ions will be strongly coupled than electrons, because if I have higher charge, maybe even lower ion temperature, they may be coupled. So plasma coupling parameter is in fact is the ratio between potential energy of ions interacting between themselves at the average distance of ion divided by their thermal parameters. So if gamma is much less than 1, it's weakly coupled plasmas, and I have a very good methods to describe the plasma. If I have a strongly coupled plasma, that it's much more challenging, and we still do not know in many cases how to do it correctly. Ideal plasma is weakly coupled, so we need to have this plasma parameter so high that even that gamma is much less than 1. So this is ideal plasma is weakly coupled. Tak. The next slide, I return to the picture that I had in the beginning. When my electrons went a little bit from the ions, there is a restoring force that it's trying the electrons to go back to ions, yes? Because my electrons are much lighter than the ions, I can, as the first approximation, say that my ions are not moving. Their mass, I can say, is infinite, so I speak only about electrons. When there are moving, I have equation of motion, yes, Newton equation, and I have the electric, the field by electric force that is restoring. Then, if I say that the velocity of electrons is just a derivative of the distance with time, so I have this equation, and it's equation of harmonic oscillator, yes? The second derivative is minus this, and I get oscillation with frequency, which is called electron plasma frequency. This frequency just grows with the square root of electron density. That is, in fact, you see your electrons restoring force are accelerated back, but when they go to the position when they are the ions, when this is neutral, there is no force, but the electrons have velocity. They go at the other side, and the restoring force. So they are oscillating this way. So the frequency of collective oscillations of electrons around ions is the plasma frequency, electron plasma frequency. Plasma frequency is the characteristic frequency of high frequency modes, collective modes in plasmas. You see this collective modes. I calculated field from Poisson equation, so I needed some collective of electrons and ions to form this field. So this is macroscopic field in the sense that it's fields on much bigger distances than interparticle distances. So I have this oscillation with this. What is very interesting, if I multiply the plasma frequency by electron, by length, I get nothing different than thermal velocity of electrons. So these three quantities are interconnected. In ideal plasmas, when the plasma parameter is high, plasma frequency is much higher than electron-ion collision frequency. Yes, so due to these oscillations are only very weakly damped to collisions. In fact, we can say that collective interaction through the macroscopic electromagnetic fields dominates over binary interaction between the charged particles. So you see it dominates. When I speak with my students that are doing at Tokamak, I say it dominates, but it doesn't mean that it doesn't exist. Yes? For example, the basic attenuation mechanism of electromagnetic wave in plasma is collisional absorption. It may be very weak, but still no absorption and weak absorption, it's fundamental difference. So, but this means in ideal plasma, the frequency of these high frequency modes is much higher than collisional frequency. So, what I have here next, yes, plasma waves. Well, if you look here, you have here planar capacitor. There is no field outside the planar capacitor. So these oscillations do not propagate. They stay in one place because there is no information in other place that these oscillations do exist, unless there is thermal motion of particles. Of course, electrons are faster than ions, so it's mainly thermal motion of electrons that propagates the information outside the capacitor. So the propagation of electron plasma wave, its longitudinal electrostatic wave, is only due to thermal velocity. You can derive it through thermal pressure, and you get such dispersion equation. Frequency of these waves is the squared is the plasma frequency squared plus 3 wave vector squared, the thermal velocity squared. Plasma waves are, of course, collisional, but often it can be a weak damping, but there is also collisional damping. It's called Landau damping. In fact, when Landau came with this damping, he has derived it using some complex analysis using Laplace transform. At the first time, plasma physicists do not believe it. They say that's well, it's some numerical, analytical, mathematical solution, but how it's in the physics. Well, I will speak about the particle and cell codes. They can verify, show how this works. Landau damping is purely kinetic effect. You cannot get Landau damping inside fluid equations because the problem is there must be some resonance particles. If you look here, you see if your k is large enough, the phase velocity is something like square root of 3 multiplied by thermal velocity, so it's often much less than the speed of light. So there may be some particles that propagate with the same velocity as is the phase velocity of the wave. So these particles see the same phase all the time. They see the field that is either accelerating them or decelerating them. Yes, so these particles are interacting resonantly with the wave. So if this phase velocity is comparable to thermal velocity, there is many particles interacting. In fact, the particles which are a little bit faster than the wave are decelerating by the wave. The particles which are a little bit slower, they are accelerating by the wave. If you have normal Maxwellian distribution, you have more particle moving slower than the wave, than the number of particles moving faster than the wave. So in that case, you accelerate more particles, you give wave give energy to more particles, then is the number of particles that is giving energy back to the wave. So you get wave damping, and you are changing the distribution function of electrons. In fact, Landau damping cannot damp out the wave completely, because then the particle distribution function is changed, and so on. So we see that the wave damping is proportional to minus derivative of the electron distribution function. In fact, this Landau damping is quite similar in the basic process to the process of acceleration in the radio frequency accelerators. In the radio frequency accelerators, you have a wave with phase velocity a little bit faster than the velocity of particles, and particles are accelerated. Of course, the wave must be damped through this. So maximum derivative is near to thermal velocity. So we have strong dampings of all waves with wavelengths less than Landau, with electron Debye lengths. We have also reverse. If you have in plasma some beam of particles going through this, in that way the derivative is positive in some part, and you generate plasma waves on the expense of energy of this beam. Yes, so this is called two-stream instability often. Yes. So now I have already mentioned that we can have a different description of plasma dynamics. One description is description using fluid methods. So in fact, in fluid methods, we use some moments of distribution function. We use density, average velocity of particles, we use temperature or internal energy, or what you would like. We have two fluid hydrodynamics, which is rare. I would speak a lot here about one fluid hydrodynamics, which in laser plasma can have often two temperatures, some radiation transport, and so on. For magnetized plasma, we can use magnetohydrodynamics description. For some effect, as I have shown the Landau damping, that they may not be enough. So in this situation, I need kinetic methods. These kinetic methods can be divided to particle methods and methods that are solving kinetic equations. So particle methods can be test particle methods, so particle in external field. I have no feedback on the fields, but in plasmas I generally have this feedback, so I have to do some feedback. I can have particle-particle methods, binary interaction included, but it's inefficient, it's suitable only for small number of particles. Then I have particle mesh methods, from which the most often used is particle in cell method. I will show, and some mesh-free methods, for example, tree codes. So kinetic methods. Solution of equation for distribution function. It's you have had, I think, in your education, Boltzmann kinetic equation. In fact, in plasmas, if plasma is collisionless, I have what is collisionless kinetic equation. It's Vlasov equation. It's a Boltzmann equation without the collision term on the right side, but Boltzmann himself thought about kinetic equation in fields that are existing outside the system. But in Vlasov equation, you have self-consistent fields that are generated by electrons, ions in the plasma. Yes, so this force includes a field which is self-consistent. Of course, if you need to put inside collisions, you can use for elastic collisions Fokker-Planck approximation of the Boltzmann collision term. In fact, because in plasma collisions with low angles dominate, so in that case you have this collision Fokker-Planck term, and if you have non-elastic collisions, you speak about solving Boltzmann equation. But what I would like to say, and I will say it later again, that if you solve particle in cell methods, you in fact solve this Vlasov equation. You solve kinetic equation, but via sampling of the distribution function via macroparticles. So you sample the distribution function, you get some noise, which is bad, but it's much more efficient, which is good. It's faster, you can solve it in all 3 dimensions and so on. So, of course, you can have also some hybrid methods, so electrons, say, are described kinetically and ions are described via fluid equation or something like that. But we often use other type of simulation that only plasma dynamics. First, if we want to do plasma dynamics or dynamics for some targets and so on, often we use we need, say, equation of state. If we have some radiation, some transport of radiation, we need opacities. We need some atomic physics rates, for example, for ionization, recombination, excitation, and so on. These can be found, they are usually found with some specialized codes, which I can call preprocessor, and there are some included into the dynamics code, often via some tables or something like that. So something can be integrated to plasma dynamics. We often include calculation of plasma ionization state. We calculate average ionization degree inside the code. In some cases, we calculate population of excitation states or nuclear processes. And then we can have some post-processor. Yes, so if I have some specialized process, which is maybe not very important or not very important to include it in all details to plasma dynamics, I can calculate it after I have finished the dynamic calculation as a post-processor and calculate what is needed. So, for example, line emission from plasmas, including detailed atom physics, I can calculate sometimes later. I can calculate, I will show K-alpha emission, including some fast electron transport inside solid target and so on. This I can calculate all after the simulation. Often I can simulate also active diagnostics result. Say I had the results from experiment with some shadowgraphy. So I can calculate the shadowgrams to generate them from my results that I have from plasma dynamics only after, and I can compare these calculated shadowgrams with the shadowgrams experimentally recorded, interferograms, and what you mean, and some other diagnostic results. So I would like to ask candidates, did you have lectures on numerics, on numerical analysis in your university? Okay, so I will try to introduce some basic things for you. If I do numerical calculation, I have 2 sources of error. One is truncation error. What it means, in my equation, as you have seen, I have some derivatives. Derivatives, it means that I use infinitely short time step or spatial step, infinitely short step. But I cannot do it numerically, usually, so I must substitute, for example, this derivative by, like you have did in analysis, but well, with some finite step. I cannot do the limit to h going to 0. I must have some small h, and if I use it, h is small, I can use Taylor expansion, and I get the derivative plus some term, which is the truncation error. So the lowest term in h that I have. I can do it in various ways. I can substitute it in this way, I can substitute it in this way. In this way, the error is proportional to h. Here, the error is proportional to h squared. So this degree alpha is the order of accuracy of the numerical method. Yes. So the highest the order of accuracy is, the faster the errors go to 0 if I go with the step to 0. So this is the truncation error. However, I have another sort of errors, which is round of error. In numerical math, my numbers are not infinitely long. They are not infinitely accurate. There are only some numbers represented. I had some step between numbers, so if I get result between the step, I do rounding, I get round of errors. So I have some number of valid digits. Yes, what is one source of errors? If you have two numbers which are quite similar, 5, this is say a 7-digit number, and I put from this number, which is 634, I get the result, which is we use in Czech comma, but English is dot, and if I do this, I get 00131. Yes, so I get 6 valid digits here, but after only one subtraction, I get 3 digits. So subtraction of nearly the same number is a very dangerous operation. I get very large round of error in one calculation. Yes, so this is the round of error. In fact, if you look here, yes, from this use from the point of truncation error, your step should be as small as possible. But if it's too small, you get here this number and this number is very similar, and you get a round of error. Yes, so that sometimes you cannot go with this step to too low number because then the round of error is high. Well-posed problem. Well-posed problem means that unique solution exists and it changes continuously with the input data. In fact, classically, you cannot solve ill-posed problems, but there are often in diagnostics, in inverse problems. For example, for inverse Abel transform, if you want to reconstruct some volume source from planar picture of this source, you get ill-posed problems. Usually you need to add some additional constraint on the solution to change ill-posed problem to well-posed problem. Well, there is another thing, well or ill-conditioned problem. it means it's already we are speaking about well-posed problems, but ill condition means that if you do some very small change in your input data, the result changes a lot. In that case, you have big problem to get the result with very good accuracy, because during the numerical solution you do some errors, truncation errors or round-off errors and so. And these small errors are like small change of the input data. So these small changes can generate big change in the result. So the condition numbers is the ratio number, is largest ratio of the relative change of the solution to the small relative change of the input data. Only some neighborhood of my input data is interesting for me. For example, solution of linear equation with matrix which is near to singular. Singular matrix would be ill-posed problem, but it need singular, it's ill-conditioned. So well-conditioned problem, it's this number is of order 1. If it's much higher order than 1, you get ill-conditioned problem. Last thing I think is the numerical stability, which is very important in task that you solve some dynamics in time from some initial conditions to go more. Numerical methods is unstable if relative error grows faster than linearly, usually exponentially with numbers of state. The numeric is due to accumulation of errors, either run-off or truncation or both. It's no. I have here one very simple example. You calculate the powers of this number, golden rate conjugate, by recursion equation. You easily find that this number, that the powers of this number fulfill this recursion equation. So if I have phi to 0 is 1, phi 1 is this number, I can calculate phi 2, from phi 2 I can phi 3, and so I should have the powers of this number. However, if I do this, I have the powers real of this number on this graph, and I have here the here the calculated numbers by this, and this one is the error. And I see in the beginning everything is okay, everything is okay. So if you have method that is unstable, you will see it only after some time. So if you do some small example, you think that everything is okay, that everything is working. After some time, your errors start to accumulate. Yes, and after some time you see that here at number n16, you firstly see on the graph that it's that there is some problem. After few others at number n20, you see that your power of the positive number is negative. So you see that it's completely wrong. Yes. And after some time, even the calculated powers start to grow. Where is the problem? The problem is that your recursion relation has another root. Has another root phi 2, and the root phi 2 is bigger in absolute value than your root. So if you calculate according this relation, in fact your solution is not only the power of this number, but you do also some small error somewhere. at least in the beginning, you see this number is infinite, and this number is not the number exactly represented by computer. Yes, so you do some error, and it means that you put here not number phi, but phi plus some very small epsilon. In each step, you get this number, which is phi to n power plus epsilon to phi 2 to the power n. After many steps, this grows much faster in absolute value than this grows. This goes even down. So after some steps, this part becomes dominant, and when this part becomes dominant, you calculate something else that you wanted. So that is the sort of the problem. That is the principle, in fact, that instability, that unstable methods, algorithms you cannot use. We will see later some. Yes. So now we get to fluid description. In fluid description, we get. We have all the density, average velocity, and thermal or kinetic internal energy. We get partial differential equations in space and time, not in velocity, how in kinetic equation. It's less computation demanding that kinetic equations can treat any state of matter. So you can do with these fluid methods global simulations, for example, of laser interacting with solid target when you have a plasma on the surface, but you have solid matter inside the target, and you get some propagation of some shock wave inside the target and so on. So, on the other hand, of course, nonlinear, say, laser-target interaction and other kinetic effects can be treated only in phenomenological way. Yes, because there are, I can put here some terms that damps this way that are damps, but I must do it in some phenomenological way. I don't have direct way to do it. Often I can have one fluid. It's often in plasma 2 temperature because the exchange of energy between electrons and ions is very slow. Well, these hydrodynamic equations are equations of hyperbolic time, of hyperbolic type. And the solution of hyperbolic equations is generally a problem. It's not so easy as elliptical and parabolic equations. And I will show it on very simple equation, which is of hyperbolic type. It's called advection equation. It's just this equation. You have some signal, and the signal is moved all the time. So to solve this equation, analytic is very simple. If you have the initial condition, the solution analytical is this solution. If you have some pulse, the pulse propagates with the velocity a without any change. Yes, so it's a very simple equation in analytic way. However, unfortunately, it's ideal equation, of course, for testing numerical methods. And I do some discretization, so I solve the equation from with some time step for some time moments, and with some spatial step with in some x that I had. So here Tn, we have equal steps. Tn is n times delta Tx, xi is I times delta x. So values of function u are approximated by discrete values u with subscripts I, which is spatial, with superscript n, it's temporal. And of course, I have, as I said, many possibilities how to write in discrete sense derivatives, how to approximate derivative. For example, in space, I can write forward derivative, backward derivative, central derivative. And how much time I do have? Half an hour? Okay. So central derivative, this is central for second derivative. And after substituting this approximation to partial differential equation, we obtain numerical scheme. So, for example, what everybody would think that is most obvious, I write this scheme. I put here forward derivative in time, yes, and central derivative in space. It's called forward time central space scheme. This works well for a heat equation for parabolic system. This can be solved, and I can get this solution for the quantity at the new time step. And what is important is this number here, which is called current Friedrichs-Lewy number, often only current number, and this defines usually the stability of the scheme. But unfortunately, this obvious scheme, forward time central state, is unstable for any current Friedrichs-Lewy number. So this scheme cannot be used. I show several other schemes for this is this FTCS. I can have upwind, which is stable for these negative numbers. Downwind, well, I could use for this equation the downwind scheme, but if I have the fluid equation, I have the sonic wave that can go both forward and both backward. Then I cannot use neither upwind nor downwind, but I can use like Friedrich scheme, which is stable for this number between 1 and -1. It's first order accuracy that I know Bart Vendrom from Los Alamos. It's a Lax-Vendrov scheme. It's second order accurate. But one thing is important to say here. If you do it, all these schemes are explicit. So you can calculate the new time step directly, this formula from the previous time step. If you put your special derivative to the new time level, you get implicit scheme. In the implicit scheme, you must solve some system of equation for the new values. But it sometimes have a big advantage because these schemes are much more stable. You can afford a much longer time step for this scheme. For example, for advection equation, if I use this scheme, it's unconditionally stable. It's stable for any time step. However, here is first order accurate. However, I don't have any explicit formula. If I looked on the solution, yes, I get this pulse in the beginning, and I should get the same pulse at the end of calculation here. If I use unstable methods, I get something like this. Yes, so my values are just oscillating there, and there is no use of unstable scheme. So these schemes are stable, but however you see that it's really difficult to reproduce the solution. This is Lax-Friedrich scheme, which is diffusive. Your pulse moves okay, but there is some viscosity inside, so you get from the narrow high pulse, you get broad low pulse after some time. Lax-Wendroff scheme is not diffusive but dispersive. It means that if you have Fourier components of your pulse, the Fourier components propagate with different velocities. So you get in the solution some oscillations. Yes? I know it's possible to combine Lax-Friedrich and Lax-Wendroff scheme basically to do it, that those two schemes eliminate there is disadvantages, and you get scheme which is much better than these classical schemes. Well, in hydrodynamics you solve Euler equations. So you solve one conservation law for mass conservation, you get momentum conservation, you get energy conservation. Of course, instead of full energy, you can write it also for internal specific energy. You need to know pressure, which is given by some equation of state. In the simplest case, you can have ideal gas equation of state, where gamma is the ideal gas constant. Eulerian methods here means that the Eulerian methods that you have static grid, that you have defined grid in the space, and you can solve this solution. All the methods we mention are typical Eulerian methods, like Friedrich, like Wendroff, and so on. In static computation, fluid moves through the static computational method in form of mass fluxes. Typically, these methods are simple to implement. The only disadvantage we will see, fixed computation mesh is not suitable for simulations where we have a significant expansion or compression, but mainly expansion of the computational domain. So I show one result of Eulerian calculation. This is calculation very known. It's Rayleigh-Taylor instability. Rayleigh-Taylor instability means if you have interface, your heavy fluid is above and light fluid is below. Yes, the interface between this fluid is unstable, because of course energetically it's more favorable to have heavy fluid below and light fluid above. It has less potential energy. Yes. So if you have this interface, and you will see in the beginning some very small perturbation. It's not planar, yes, small perturbation of planar interface. The perturbation grows in time. Still in the case it's a linear case, so you could calculate one sinusoidal profile, but after some time it starts to be non-linear, and you see how it evolves. It evolves sometimes like what you can be seen, the pictures from explosion of atomic bombs. Some here, this shape and later this chain evolves more. So if you have two fluids, the simulation domain do not evolve in too big evolution. You can you will use Eulerian code, and Eulerian code is classical. Well, you can do another thing. If I will show why here. If, for example, here the laser was incident from above on the foil, which was 5 micron thick. Well, it's from our simulation of experimented pulse, and after some time you see here evolution of the foil. Yes, foil was 5 micron, and now I have 1 millimeter of plasma generated from the foil. So if it's in cylindrical coordinates here, so this is the distance r from the axis is distant from the foil, and you see that my domain is very big, and I had to have here in the beginning very fine mesh. Yes, here I should have at the front side of the foil mesh, which is less than say 1/10 of micron, even less. So if I put such a mesh to whole space, it would be very inefficient to calculate it in Eulerian way. So I go back, so I can write it in such way. So I have substituted instead of Eulerian derivative, total derivative, and I take coordinates which move with the fluid. So I must solve additionally equation which calculates the motion of the nodes of the mesh, but I have no flux between the cells. Yes, mesh is connected with the fluids. So when very small in the beginning, mesh cell expands very much. Yes, I have still one mesh cells, so the mesh cell is in fact adequate to the expansion that's here. So mass is constant in each cell, and this is Lagrangian calculation. I would like to show some very small example. You will see some point explosion, like atomic bomb. It was solved analytically by Sedov, so it's called Sedov problem, and it's a very good test because you know the analytic solution. You can see whether your shock wave, which is moving with the proper velocity. But what's very important for this problem, that really the shock waves move spherically. Yes, that it's rounded. In the beginning, not all in my mesh here, not all the directions are equivalent, but still I have to get results that is nice in this way, cylindrical expanding wave, or spherical expanding wave. So this might be circular, quite good test for the programs. You have seen that everything, for example, you get here compression, so the cells became smaller. You get here expansion, your cells get bigger. So in 1D, Lagrangian is excellent every time. In more dimension, there is a problem with Lagrangian. The problem is shear. if I have some cell, yes, and this part moves this way, and this part moves this way, I get some cell which vice versa, which looks like this. It's not with self-computation. Yes? So for this is solution, so-called arbitrary Lagrangian Eulerian method that I will see. So for me, this is experiment at pulse laser in Prague, simulation laser coming here. Here is the target, the foil. There was a circular spot of the target. The target was heating. Front side was expanding. From the expanding part into the target, there goes pressure. So there goes a shock wave going there. And if the shock wave moves to the rear surface of the foil, rear surface of the foil start to move. So you get here the expansion, you get here a motion of the backside. You will see the target was aluminum. Aluminum density is solid aluminum 2.7 grams per cubic centimeter. We got here maximum density something like 5 gram per cubic centimeter. So we have compressed aluminum about twice. No problem for laser. This is the temperature we get here. It's after the maximum of the laser pulse, we get here the maximum some 1.2 kilo electron volts of the temperature, and we have here spectrograph in this direction. Tangentially to the target, and we were observing spectra time integrated, but with spatial resolution. And what was interesting for us was this part behind the target, because it's dense, not very hot temperature plasmas, and we were studying these light. It's a high series of hydrogen-like aluminum. So aluminum were only one bound electrons states, and here alpha means transition from the second level to first level, beta from third to 1, gamma from 4 to 1, so it's 5 to 1, 6 to 1, 7 to 1, and this is ionization edge. In fact, you cannot see higher lines because the plasma is dense, and higher states are in fact shifted to continuum. It's difficult to model it, but it's not important here. So this is what I did. Okay. So this was okay, but if you get something like this, you can get to the situation that it goes to this, and you get negative volume of a cell, and your simulation fails. The modern method is to use arbitrary Lagrangian method. It means you do Lagrangian calculation for a few steps, and then you do some rezoning, so mesh untangling and improvement, and you do remapping, so you do conservation